do you sort yourself into different groups of people? So probably you will interact with different people now that you see what their postures are like, so that will be interesting. So we're going to move on with the tissue optics. And Igor.
Okay, so I just want to say that those of you who have mobile phones, you can check this online solution on your mobile. If you put in your mobile Biophotonics.fi, you will see that's Monte Carlo, and you can see the calculations easily on your mobile phone. So if you want to, so just Martin is just, for people to have a look on that. So, and I'm sorry for that because of no internet connection, I'm not able to demonstrate it with on the screen here. Again, let's back to this polarized light. And I just want to remind you the basic physics about this polarized light. Okay, so if we consider how this the polarized light is interact with the medium, so, and let's say first that we consider just how the light reflects and refracts on the boundary of the say transparent medium. So, and if we want to, when we consider just the light, let's say in the Monte Carlo that I'm describing earlier, so we don't care about the polarization, and we used just simply Fresnel reflection coefficient, and we're able to count it based on the difference of refractive and refractive indices. When we consider the polarized light and interaction we see again with the medium, we also should, based on the Fresnel equations, and we should consider independently the transverse electric or transverse magnetic components, or if when we operate in our Monte Carlo, we're trying to, or our model, so we're trying to link these components to X and Y components, just for simplicity. And here is the simple reflectance coefficients that shows for these two components, T and Tm. And you see, so that depending on the angle of incidence, so we will have the slightly different reflection coefficients. And this for when the light is coming from the medium with lower reflective index to the higher reflective index, like for example 1 and 1.5. And here, when the light is from the reflective index with 1.5 to 1, is from the higher to smaller. And here we're able to see that here we have total reflection on the boundary, on the particular angle, and here is also the difference. So and basically, when we think about this reflection and refraction of this polarized light, we mostly, consider this point is known that after this angle of incidence, nothing will propagate through, everything will be reflected. But there's also another important parameter that known as a phase. So that means it's a phase between this X and Y component of Tm and T. So thus, if we consider when they see what happened about this phase for these two cases, again we will have for one case when the reflective index is higher and smaller, coming from the small to higher. So we will see for one component there is no phase shift, and then there will be shift, like that. And vice versa for another one, so we will see the again phase shift when it's coming from the higher to the smaller refractive index media. So they will be defined with this component, and it could be summarized with this equation. And what does it mean really? So imagine if we consider the wave that have a certain okay, state of polarization here, and we consider S and P components. When this wave come into the medium boundary, and when it reflects, so we have the situation when one component is changed the phase and one will be preserved the phase. And when it propagates through, so we also should be able to estimate how the amplitude is changing here and there, but also depending on the angle of incidence, so we're able to see some changes. And what does it mean? Oops. Okay, that means, okay, here, that if we send, let's say, the, right circularly polarized light, when we have the certain shift between, phase shift between X and Y component, and when it reflects here, so because of phase shift, we will see the changes of helicity from right circular polarization to the left circular polarized light. Okay, and if it propagates through the medium, it will preserve that helicity. That's only based on that equations. Okay, and thus, if we think how the light polarized light propagates through the sample, so we send the, again, circular polarized light, when it's reflected, it's changed. When it propagates, it's preserved. Okay? And interesting fact that when we consider the scattering of light, for example, here, let's say, for simplicity on the release scattering, it will be also some phase shifts due to scattering. Thus, when the incident light, let's say, again, right circular polarized light, scattered back, it will be flipped with the helicity and becomes left circular polarized light. And when it's scattered forward here, it will be preserved helicity. And what does it mean? That means, so if we consider scattering medium, so and we illuminate the medium with the right circular polarized light, and the light is reflected on the boundary, it's changed the helicity. If it propagates through, it's preserved. Then let's say it's scattered forward, it's preserved helicity. If it's scattered back, it's changed helicity. If it's scattered forward, preserved, and then coming out, and you see, it's also will change helicity. So if the other scenario, so it's scattered forward and scattered forward, scattered forward, scattered forward, and it will preserve helicity. And there also the time when it's scattered several times back, and it will again preserve helicity. And thus, if we want to count, what polarization state will be then, so we should simply consider even and odd numbers of helicity flips. And on the other hand, what we can say about that, so if we do the illumination of the scattering medium with the circularly polarized light, and that means that the light that coming out to the detector will have two components basically, right circularly polarized light and left circularly polarized light, because of this helicity flips. And then if these two portion of light is similar, the product of them on the detector is equal, will give us the linear polarization, because the equal and this constructive, destructive interference will produce us linear polarization. But on the other hand, if one of the portion is prevail against the other, so we will have elliptical polarized light, or if one is, negligible, so we will see again the circularly polarized light. And you might ask me, so okay, who cares about that? And there is one of the ideas that we tested. So imagine if we consider the tissue in terms of light scattering. So there was enough evidence that when the tissue are normal conditions, and if we consider the cell and what actually, what the cell's parts are scattered the light, basically it's a nucleus. And if we consider normal cells, so they are very much as a mean scattering regime. And what means mean scattering regime? So it means that it's roughly equally scattered forward and scattered back. And that means for a least scattering cell, we will roughly have equal number of circularly polarized light and left circularly polarized light. And for normal tissues means that we expect that the signature of light on the detector will be close to the line of polarization. However, when the cancer is coming, so what we know basically is the DNA is changed, and if DNA is changed somehow, so we assume that refractive index should change because of the electric constant, it varies with the changes. Anyway, so even if the size is the same, but refractive index is changed, or very often the size of nucleus is changed up to 2 times, so the scattering becomes not mean, it's more, sorry, not release scattering, it becomes mean scattering. And mean scattering is, as we considered in the previous part, is more forward scattering. And here, if we look at this scattering function that is okay, wait a second. Okay, you see, so here we have the forward scattering peak, and thus there will be more preservation of helicity when light is propagated through. And thus we should see more light that will be prevail with one or another helicity. It means that we will not see the linear polarization, but we will see more elliptical one. That's, of course, very primitive explanation. If we want to consider it any more precisely, so we should come and consider the, let's say, the Stokes vector. So, and I'm just will remind you what does it mean. Okay, so what is the Stokes vector? So when we consider the polarized light, so we want to know, okay, so we want to characterize the polarization. And very often we use the Poincare sphere as a graphical tool that able to show us the all stages of polarization. And how it works, so we can be able to assign sort of vector that called Stokes vector, and then these elements of Stokes vector, they relate to the actual parameters or measurements of intensity. So if we measure the core, let's say, and cross, if we measure core and cross polarized light, and the sum of them will give us the first parameter in the Stokes vector, and the difference will give us second. So, and then if we rotate the analyzer for 45 degrees and do the same differentiation of the measurement with the 45 degree rotation, so we will measure the third one, and with the addition of photoelectric plate to see is it right circular or left circular polarized light, we're able to find the this fourth element of the Stokes vector. And you see, so this element is show us in our hypothesis, so where the flip is happening, that way or that way. And thus, with these elements, we're able to describe all possible state of polarization. And these elements could be presented in terms of 3D case as a Poincare sphere, and thus we know if the these elements show us this point, we know that it's perfectly circular polarized light. If it's on the equator, it shows us linear polarization. If on other pole, it's again, if here is the right circle, the left circle, and between this areas of this will be elliptically polarized light. And then, if I want to describe how this polarized light propagates through the medium, so the standard approach always, so we have the incident light with known Stokes vector. And we can measure, physically we're able to measure the light that's coming out, and we're also able to define in a similar manner the Stokes parameter of light that's coming out. And then we want to know, okay, what happened within the medium. And what happened within the medium is described by so-called Müller matrix that have here, for example, 16 elements. And what now we do, and many others do, we're trying to understand, okay, so, oh, sorry. What each element is responsible within the tissue. And when we started like a conversation on the previous part, okay, what is the optical properties? And when Martin demonstrated with his slides, you know, how it changed from the single scattering to multiple scatterings. So each element of Müller matrix or Müller matrix itself, it could be also be interpreted in terms of property of tissue or instrument that describes tissue optics. The point only is, if it's homogeneous medium, means that the distribution of all scattering particles within the tissue is equal, let's say. So that might be the good way to describe. But however, if we have multi-layered mediums, so then big question, okay, so what each element of Müller matrix means. So because how we can able to say why the polarization is changed, because of scattering, or because reflection on the boundary between the medium, or due to birefringence, as we discussed also briefly, or due to something else. Okay, and now again the community trying to work out and find out, you know, how we can use these elements for the quantitative tissue analysis, and there's some success, but there also the important issue that I want to mention here is another one. Okay, so if we want to consider in the right way how the polarized light is scattered, we consider the incident light and scattered light. We're able to again to link it with the particular scattering phase function. And here, you see, so on the previous slide when we saw this forward scattering, there was a mean phase function presented in the polar coordinates. Here we have this logarithmic and another way to show via the cosine of scattering angle here. And for the different size of particles, we will see also that, or in terms of cosine function, we will see that intensity will fluctuate with for different scattering angle. I will see different forward and back scattering, for example, here. And thus, when I plot coherently with that, I plot the Stokes vector that show me the flip of helicity due to scattering. And you see, when we consider like the release scattering originally, so I mentioned that okay, scattered forward, change helicity, scattered back, scattered back, change helicity, scattered forward, preserve helicity. In reality, when we consider changes of size of particles, so there will be a number of flips, and it doesn't mean that it's more complicated. It means with a different angle, they should be for particular size. It could be many helicity flips. When we started for the small particle, so initial one, they just scattered back and scattered forward, important. But here, you see we have number of peaks, and each peak represents as helicity change. Thus, the propagation of the scattered light, I mean circular polarized light, will have a more, let's say, complex dependence on scattering angle. Okay, so, and to make then interpretation of our results in terms of measurements, we should be absolutely sure about experiment to make sure that we have no artificial, results, like here, for example. And we started to implement this changes of size in a model, and we found really that, okay, so if we consider in terms of scattering events, so we will able to see for preserving of helicity on a Poincare sphere, and it is this fraction of photon that will preserve helicity will be different for different again scattering events, and we're able to precisely calculate it. So I will show a bit later why it's important, but here what is important is that we're able to implement all these angles parameters in the model that we have. So the other important issue that when we consider the polarized light, so and we consider that on the detector, and as was mentioned yesterday by Kishan, for example, in his talk. So when we have two waves that have a same wave number, again, but different detection and different phase, so we should consider what will be the superposition. Yeah, thank you. Okay, so and we just here consider two waves, and from the simple mathematics, so we can show that, okay, so we're able to prescribe here the interference term, and which is important, and in a way that, again, with a continuation of some algebra, so we're able to define this phase difference and come to the form that describe the interference of two plane waves. Okay, so and in a practical way, again, so if we consider constructive and destructive interference, we have okay, so I think it's better to show this. We have, for example, when it's here, so we can doubling or addition of these two amplitudes, we have zero, and we have intermediate case. And if we consider the waves, so we will always have some, let's say, sort of fluctuations. The other important issue here is the coherence. I will have a talk about coherence just a bit more in detail in the next part. But here what I want to say in a mathematical point of view, so when we consider the interference of two waves, so we should add here the term that relates the path length or path length difference between two waves with a coherent length. And it is if we have the coherence length with which is very small, so these terms becomes zero, and we have only that part that gives us the actual signal. But if it's long enough, it will be like this term will be close to unity, and thus we should seriously take into account this interference term. And in a practice, if we do this, let's say, counting of interference of many waves together, so if we have short coherence length, we will have much clear vision, and the other will produce sort of speckles or these fluctuations at the solenoid waves. And if we talk about this fiber optics geometry, so we should carefully then select the distance between source and detector to make sure that the path length difference here will give us the appropriate parameter in terms of fluctuations. But very often when we use the CCD camera, that will produce a number of speckles, and they will fluctuate in time depending again on your detector conditions. Okay, so, and here is another picture which is maybe looks similar on the previous, but we did it calculation of Monte Carlo with a non-analytical solution. An analytical solution assumes that the light is incoherent, and we put this incoherence, and we're able to simulate the same thing, but again with the influence of coherence properties of light. But this again like scattering of light of core and cross-polarized light and the polarization ratio. And all these parameters could be easily counted, and I mean not easily but relatively easily counted analytically for the simple homogeneous medium, and can be considered with modeling studies. So the other important issue is for the issues that is also not considered often is the roughness of the surface. So you see, so depending on the roughness, so we will have also changes of phase and polarization of light, as described like in the previous slide. So, and thus, when we illuminate the actual tissue, for example, skin, so we're not able, again, say for sure, okay, so how this depolarization is happening. So, what is more influenced, the roughness of the surface or scattering of tissues? And we try to, let's say, to analyze that and see, okay, what happened if we consider the phantoms with a certain roughness of this parameter we used as a definition of roughness. Basically, it shows the average, size of let's say the deviation from the 0 point, means how the roughness is big enough, let's say. Okay, and we found that, okay, so that we're able to see and compare this for two different phantoms that we also tested experimentally. And this is with different roughness, the let's say the path length distribution within the tissues will be not the same. And if we see the analogy of depolarization ratio within the tissue, that also will have a difference. Means that the depolarization of light here and there relates very much on only roughness as well. So, and all these issues we implemented again to this Monte Carlo that I'm describing earlier. So, and we found the known phenomena like a helicity fleet. Imagine, so when we illuminate the medium and see the semi-infinite medium, and we see the backscattered light, so we're able to see here the increase of the cross-polarized light, and here like sort of decrease. So what does it mean? So if we send the let's say right circle polarized light, and it's propagate forward, then flipped and propagate back, so light is coming on the straightforward back direction, we see with a flip, but those light that coming outside will change the helicity. So that's also known and predicted theoretically phenomena. So, and how do we know that we write in this modeling and description of our, let's say, polarization propagation through the medium? Okay, so here is a slide that shows us the changes of polarization for the counted for the scattering medium with the actual diameter of the scattering particles. And you see, so we for the different size, so the helicity is slightly changed, and we will see the changes with the ellipticity of detected light. And we did the same measurements for exactly same, let's say, medium with the same properties by using the microspheres. And we found that our calculations for the homogeneous medium with the semi-infinite is exactly overlapping or coincident with our calculations. And again, here we use the Poincare sphere for the explanation of results in a graphical tool. And then this is actually the experimental result that we used. So you see, so it's the first idea was to understand, okay, so how the light is flipping, and we did a number of measurements to variate this distance between light source and detector, so, and we were able to make it from the same point and then separate it, and the separation here is done with a very simple idea, so that to reduce the portion of light that flipped on the surface due to reflection. And thus we're able to consider only those light that during flips within the medium due to scattering. And okay, so we found the wavelength for particular position of let's say illumination part of source, light source, and detector will have the predictable changes of the polarized light on the detector, and we're able then to characterize, okay, so what happened. So if we know that for certain amount of particles here, the helicity changed one or another way on a Poincare sphere, we can say qualitatively, okay, so is this increasing the size or decreasing the size? And then we're trying to use this technique for optical biopsy. Again, with this, with the main idea to characterize the tissues. When I mentioned on the previous slide that, okay, the nuclear size could be increased due to cancer, so potentially this technique obviously able to be used for experimental assessment of that. And now just a few words about this optical biopsy. Obviously, so we're trying to develop the simple technique for optical biopsy with that and characterization of tissues. So, okay, what is the optical biopsy? Do you know? How many of you are aware what is that? Okay, what is that?
It is to do it's to look at the histology of tissue without actually cutting it and taking it.
Yeah, and how they do that in practice? You know?
I'm familiar with microscopy, like confocal endomicroscopy to do that. There are also other sorts of endomicroscopes based on two photon and non-linear ways.
Yeah, but what is the practice, current practice, you know?
Oh, you shine the tissue with light.
And you know, it's not like that. So what I found, because when we develop, when we talk about this Philips technology with the tumor, so when we came to doctors, clinical doctors, they said we don't need it at all. So we don't want to spend money for something which is expensive and less useful. And then, before we started to do anything, I mean development, we started to talk to clinicians first and to find out, okay, what they really need. And when we came with this idea saying, okay, we're potentially able to see cancer, non-cancer with this simple device. They're saying, well, okay, so, and do you know how it works? And so we said, okay, how it works. And they explained it. So the current practice in most of the countries, as my understanding is, you have like the patient that has suspicious of what happened on the skin or somewhere else. And he's coming to the doctor, basically to general practitioner, not to the hospital directly, to the general practitioner. The general practitioner, don't care, so he's not sure what is that at all because he's not trained enough. And what he will do, he will simply cut the piece of your tissue and send it to the laboratory. The laboratory is not the hospital, so it's like they basically, hospitals use the laboratories like outsourcing, organization, to help them. So it means they will cut the piece of tissue and then put it on this cassette, for example, the one of the way, and then put it in a paraffin and prepare this paraffin embedded tissue work. And they do it with many tissues. It doesn't matter what tissue, so skin, it could be liver, it could be stomach, and everything when it's taken, the piece of tissue will be prepared with this paraffin embedded tissue box. And then they will send it to the laboratory. And in the laboratory, they will, using this microtome device, they will cut it very carefully and prepare the very thin slides, 3 to 5 microns. And with these slides, they will produce this histology microscopy slides and will pass it for investigation in a microscopy. That I think you come into that stage, avoiding the previous ones. But when we consider the creation of that slides, so it's not actually simple. So if you're trying to create the slides, you might have some missing or lost tissue spots to prepare the right slide for this microscopy use. And thus, it requires some time and facilities, and again, some people who should prepare these slides. And then also, okay, so when your biopsy samples, not yours, but someone's biopsy samples are reviewed, so sometimes it's very difficult to say, okay, so is it cancer, non-cancer, and also it requires training of other people who just come into this profession, to understand what is that. And also, because we have basically a number of people who want to find out, is it cancer, non-cancer, what is that really? So there will be a huge amount of slides, and as a reality, we have the queue and cost and delay in treatment and some disappointment of patients and many, many other issues. Okay, so that's the reality. But when I spoke with these physicians, okay, so how they know is it cancer or non-cancer? And they basically will show some slides like that and say one is cancer and one is not. So how do we know which is cancer? And when I'm asked the physicians, how do you know what is cancer? Which one? Show me. And she said, well, I have 20 years experience, and I know. I said, I have no experience at all. Tell me the secret. Which one is cancer? And she said, well, when we look at these slides, we see if the boundary is clean enough, if the density of nucleus is not high enough, and many, many parameters they can see. But what I understood really, so that they consideration is very subjective. So means that they're not able to, for some samples, they're not able to say for sure is it cancer or non-cancer. But on the other hand, I understood that, okay, if that guy is able to just with simple microscopy, means with the magnification of images, they're able to say cancer, non-cancer, that we're potentially able to develop a technology that could be automatically define cancer, non-cancer, or pre-cancer, or something like, or at least differentiate non-cancer, cancer when it's clear. And thus we're able to reduce cost, Q, and some treatment, and procedure will be increased. And thus we started to test our, oops. Okay, wait a second, something, okay. Okay, so, and we started to use our simple technique for this box. So again, we send this circular polarized light, and we measure how the light propagates through these tissues on the block. We're not slicing that, on the thick tissues. And we're trying to, again, use the Poincare sphere as a graphical tool to make a judgment, so is it cancer or non-cancer. And what we found really, so we see this Poincare sphere, so when we have two components, left and right, so for the normal tissue they will really produce this stage of polarization that will be close to equator. And for those that more cancer, so they will be distributed on a, again, more randomly on a Poincare sphere. As a result, we will see the elliptical light. So that's, for example, the result of actual measurements on a different position of one sensor, this one cancer, and that non-cancer, and we're able to see the difference clearly on the Poincare sphere. And then the way how to calibrate the position of Poincare sphere to make sure that we always measure on the right point. So because if your initial light or detected light is differentiated, these points could migrate on the Poincare sphere there on another way. But finally, so we demonstrated that it's it's possible to differentiate clearly with the calibration on the microspheres. And here, for example, the results of measurements on the Poincare sphere that linked with histology, and that we're able to show the places when we scanned the tissue block and show the cancer and non-cancer. And when we came to this, our clinical partners, the guy who is like a professor and he always, do this assessment of cancer, he didn't believe us. He said it's impossible. And he gave us like set of 10 blocks and said, please give me the answer. And we gave him the very similar pictures like that, so marking cancer and non-cancer, and he was quite surprised, and he gave us another 10, and we again gave him the answer, and he said that in all the cases we was very much correct with that assessment. But he was a bit worried that, okay, so if in reality we develop finally the technique that will be used in clinics, so there will be a number of job losses that people who are working with this, with these assessments. But we, at the moment, we don't try to, to go that way because obviously for clinical application we need to confirm the specificity and selectivity of the technique. Do you have a question?
What's your degree of accuracy?
Right, that's uncommon. Right. So, and in our case, we have not much, let's say, samples to test for the particular cancers to answer for sure. So thus, at the moment, we do collection studies like to when the new samples can be given us, so we use it for statistical point of view. But what I can say that some our other results shows that this technique is also able to see the aggressiveness of the cancer. So we're able to differentiate potentially the again, more or less normal, like pre-cancer and cancer. So of course it's not the final stage, so we're still working, and there's a number of issues that we should answer. But main of course is problem is statistics, so we need more patients basically. Okay, so and in the next step, so as I said, so we want to develop the new technique, and we think that with the next step we will be able to come to the in vivo measurement. So the only thing, so we need to find a way what should be the probe or endoscope of that. So the actual problem at this moment that there is no any fiber optics that can preserve the circularly polarized light, and potentially we can make it with this laser diode. So, but there's our number of our work is focused on the creation of a device that we can adopt for the in vivo measurements. So, but those of you who have an interest in the details, so you can have a look at this paper in the Biophotonics that was published last year, when we describe this development of this technique and then more in the details. And we also did a number of comparison, and we was very lucky at that time because the Steve Jacques, who joined our research team that time, he tested our result on his own code, and he was satisfied with our, let's say, conclusions, and help us a bit with the, let's say, to increase, to clarify the discussion in the paper. So the reason is, you know, that when you consider or describe the propagation of light within the tissues, so there's a different communities who do that. As I showed on the one of the first slides, we have the possibility to describe it in terms of, let's say, Boltzmann equation, in terms of Maxwell equation, in terms of stochastic modeling, in terms of, let's say, beta-salpeter equation, and some others. So, and all these communities have their own, let's say, key parameters or key stories, and sometimes when we even talk about the same phenomena, the people could not understand each other because they're using different description of the same thing. So we should do the standardization. So, and also Kishan yesterday mentioned about this more complex light, like Lager-Gaussian beams. And we're also trying to implement these beams for this similar sort of diagnostic with this simple purpose. So imagine when we consider this Lager-Gaussian beam, we're able to consider different state of polarization only one cross section. And thus, when illuminating the tissues, potentially we think that we're able to see not only the changes of one of, let's say, state, but the other could be changed as well. And why it's important? So imagine when we consider tissue, we don't know a priori its property. So there could be some birefringence property, and if it's birefringent, so depending on the position of my sample, so the polarization signature that's scattered back could be significantly different because of this polarized light when the orientation of axes are different. And thus, when we have a number of polarization states, so we're able to see that one will change that way, another that way, and if we know the, let's say, uniform changes of this polarization due to birefringence and other phenomena, so potentially using, we call it like a color-coded high-order Poincare sphere, or we now transfer to high-order Poincare sphere, means that each point could be associated with a color and show us the state of polarization, which could be linked with the, or compared with those that is coming in. So for this studies, so we have the number of results, but they're not yet for the cancer tissue, so mostly some modeling, and we're trying to prove the concept that this idea can be transferred to the cancer detection. So it might be too early yet to show any results on here, so we will maybe first show something on the next Photonics West conference. Okay, so and now what I want to say, so that in terms of tissue optics, so and when we consider, let's say, the single to multiple scattering, so the optical properties that we're talking about, we should clearly define, so what actually we see and what the conditions, experimental conditions are important. And obviously when we use the focus light and when we use the diffuse light for fiber optics, they say let's say the probing geometry is not the same. And thus, if we add the coherent properties of light that I will show in the next part of my talk, so are also important. But and we know that when the coherent light propagates through the medium, the coherent properties could be changed. But we're not talking about that much. So we assume that, for example, lucidity is constant. And some issues also that might be not considered, but again, so what I want to say that when we consider tissue optics in terms of scattering, absorption, let's say the anisotropy of scattering or size form factor of scattering particles and refractive index. So even if we switch to the polarization optics, so we should consider it we see in terms of polarized light and its interaction, and which is not similar with the let's say we call scalar optics when we don't consider vector nature of light, like polarization. So, and this part I will stop on here. So we continue this studies, and we'll show some results later. So when we're ready with that.
Okay, thank you so much for that, Igor. So we're beginning to see now that when you go from microscopy into real tissue, the problems that arise and some of the solutions that are brought about by people like Igor and Steve and so on. So not just in the modeling of it and understanding it, which of course you need to have if you are to develop those solutions. So I think you're all here, many of you, probably 2/3 of you, trying to solve these kinds of problems. How do you image or sense in these kind of turbid media? And one of the things that has been mentioned before, possibly by Kishan, is always remember it should be fit for purpose, right? That's the key thing. There is no need to have 10 nanometer resolution if 100 nanometer is good enough, or even 1 micron resolution if 50 micron resolution is good enough. So you need to think about it in those terms. What does really the clinician need? And so when we talk about this, again, we're presented with an instrument now that has been tried out in 20 cases, I think you said, clinically, and seems to produce good results. But there is another step to get that approved and generally used in the community. And we find that a lot of these technologies, some of them get stuck at that point. Hopefully this one will not. But we will see. But do we have questions? Yes, we have a question.
Do you see this optical biopsy as like a replacement of the traditional
doctor?
This optical biopsy, do you see that as a replacement of the doctor's diagnosis, or more like a tool for increase the effectiveness in the diagnosis?
Well, I'm very positive that optical biopsy can be developed on the, on the final stage. But again, even now, so if we can provide the, let's say, the clinicians with a tool that will minimize their time or help them to decide that, okay, definitely no cancer. Okay, you don't need to cut your tissue, so go home. So if it's like, will show definitely cancer, okay, definitely cut. And they could be just some cases that's cancer or non-cancer, and in that case they can use the more, let's say, sophisticated, technologies with some fluorescence, with something. But initial assessment that could be just done just really, simply with a GP, not in a hospital. That will save a lot of time for healthcare in general. So also, if it could be developed like on a very reasonable price, imagine if someone can buy it in a pharmacy, like, and if coming from the hot countries like, I don't know, Israel or Australia or some other, and then seeing on the skin the spot and not sure is it melanoma, non-melanoma, what, you panic or not, so just and simply can check and say, okay, definitely not, or you should see the doctor. So the indicator like that, it could be very simple, tool for the community.
So the first goal is to avoid unnecessary biopsy.
Well, if it's not cancer, so why do you need the biopsy? Because what they do really at the moment, so they don't want to make a mistake. They will cut not 1 centimeter of your tissue, but quite big amount, and send it to make sure that they cut it enough and took this might be possible metastasis, whatever. So, and send it to the doctor. And for some patients, like especially for kids, and it's quite high rate for teenagers, for example, about 15, 16 years when this melanoma could be developed on the skin. It's painful really, and then they feel in themselves that okay, they with cancer, and thus when some indicator shows okay that it's non-cancer, it will be even like say psychological effect that they will save them not be depressed for that reason. So thus we're working on developing different like optical biopsy techniques, and this is just one of possible. It's simple and cheap. Okay, but again, so of course it's not final solution, so possibly so we can do some more advanced one. Yes.
I remember reading that another group had done polarimetric monomatrix. I think it's Novikova,
Yes.
Validet.
Yes.
And how does this method then compare to that one?
Okay, I'm actually visiting professor in Novikova's group.
Okay.
So, and I can answer your question. So, okay, so they have a bit different approach. So, okay, so when I'm just wait a second. Okay, what they vision. They come in also from engineering point of view, so, and if you know, they work in the École Polytechnique in Polyzou, and this place, it's like a very cool place actually. So, and this engineering school that produce military engineers. And originally they worked with and started with a number of collaboration with Horrible, who developed first polarimeters. And they consideration of all that problem coming from polarimetry issue means means that they know incident vector, Stokes vector, and then able to measure the vector that coming in. And then they investigating all these elements of Müller matrix. And what they do, they try with the simulation to find, okay, so if they eliminate the, let's say, medium with the different angles or different positioning, so how these elements will be changed. And that they trying to do sort of calibration to find that, okay, if my measured vector is changed like that, and I see that these elements change that way, so this will be goes to cancer, or this will be not to cancer. So they analyze the Müller matrix elements. Our approach is more coming from the Jones formalism, when we consider how the polarization state is changed within the medium, and we can predict it with, let's say, Monte Carlo analysis, and then we use it to understand, okay, how the signature is changed on the Poincare sphere. So if we would, let's say, if we use our technique, that's what we're trying to compare, so we're able from our technique also to count or extract some Müller elements, and we do comparison to cross-validate the techniques. So, but initially they have different philosophy compared to us. We focus maybe on a more, like, to develop this simple optical diagnosis. They take it a bit more general, and they also use the technique that we say using camera, not necessarily the fiber optics or focus light as we do. So, and thus also each element here have roughness influence, have some, you know, layers, so that they not a priori answer, you know, how it's influenced the actual measurement.
So I have another question. How long does it take to acquire the matrix when you do this measurement? How long does it take to do the measurement?
For this one?
Or your method?
Okay, our at the moment is very slow. I have no this, well, not quick, I would say. So we do at the moment the, let's say, mechanical scanning of the sample. So we consider this to use the Galvan optics, so maybe use the other engineering technique. But we, at the moment, we're trying to prove the concept that we're able to see the changes of circular polarized light on Poincare sphere as a key measure of cancer, the cancer stage, not the actual device for, you know, how quick we can do the measurements. They do, of course, much quicker because they one shot.
Right. So therefore, how quickly do you need to do it to remove motion artifacts? If a person moves, or
right.
If you're talking about taking this
home.
Yeah. So if I go home and if I'm doing
sure.
So how
okay, so at the moment we do mostly for these tissue blocks, and we think that the first implementation of the technique could be to help the how to say this pathologists or the people who you know do this analysis of cancer, non-cancer. So it will be like an extension of microscopy that they will see with microscopy first on the block, let's say, and then they will pre-select blocks that definitely cancer, non-cancer, and then use this microton machine, for example. For the in vivo measurement, so we think that it should be the holder, that it should be placed on a tissue to avoid this vibration. And of course, there's still number of discussion what should be final design of that. But it's like a target. So we're not coming on the stage to see the motion artifacts. But for the circularly polarized light, it's not an issue. We think that there will be complication for this like a Gaussian beams, because they have like a phase, and this phase changes more influenced by any vibration, even vibration, not only vibration, but vibration of the system as well. So that's the most.
Yeah, but even without the polarization effects, I mean, generally imaging, this was, I suppose, one good way of looking at this was is when they started off motion pictures. They came up with the idea that 16 frames per second was a reasonable way to represent, you know, normal human motion. So it's not going to work for Usain Bolt, but you know, the rest of us hanging around there. Assuming if you take a person and maybe you have a resolution of the order of 50 microns, or maybe a little better than that, so 16 frames per second is okay. Once you start to go to smaller resolutions, then you need a higher frame rate, just because the smaller motions are going to happen in that sort of time frame. So I think that's maybe a very crude way of looking at it, but at least to give you some start.
Yeah. You ask very strong questions, because in the polarization case, I don't think that many people will answer that how to avoid this superficial motion, because it's of course they're more sensitive for that.
Yeah, but your intensity is going to be a problem anyway, even if polarization is what you're looking for.
I was going to say that motion presumably will be more of a problem if you're looking at degree of polarization and depolarization type effects.
Yeah, absolutely right. So we always put the three ones co-across the polarizer. Yeah, even in terms of Stokes parameter, just to make sure to see, which parameter we can use as a quantitative one for the final.
There was a company in Australia, did you come across them? Polarimetrics, I think they were called.
Oh, they number them.
Oh, okay.
It's not only one.
Right, for skin cancer, they were making a device for skin cancer using polarization.
Yeah. So there are many companies that trying to go there. For example, we work with Biophotonics. That's a company from Israel, and they quite good company in terms of quite successful. They got a startup, and then they've got the very high project from I think United Nations. So what they developed this simple the device based on the mobile phone, like with an extension, to see the cervical cancer. And they do these tests in Africa for this, in a different place, because it's like mobile phone and a little extension. And now they want to implement this polarization to enhance the selectivity for that. And actually, it's also the company is organized by former PhD student of Steve Jacques, David Lenz.
Yeah.
So we have this community of workers.
So he used to call that company Mobile OCT, but then he realized that doing it with OCT on a mobile is quite difficult, so now they call it something slightly
About
ODT, they call it now. Yeah, so they've had to change the name.
So we work with him so to further develop this.
So is there any statistics in terms of success with that type of technique versus a more sophisticated?
Okay, so we do
you really need to do the sophisticated stuff, I suppose?
That's the right question. So we do most of the statistics based on our collaboration with France, because they have an actual couple of clinics, and when they do the tests of the unit matrix-based system, and we in parallel do ours. And this is a nice cross-validation of the technique as well. So I can't say that it's very quick way to do. So we're working like 2 years, I think, at the moment jointly. But there are too many bureaucratic issues that should be worked. In reality, the actual clinical trials we do maybe months per year, not like straightforward. So, but it's only because of some bureaucratic issues. So we would like to do it quicker, but again, so looking for opportunity.
So Barbara has a question.
Do you think your method has the possibility to tell apart different types of cancer?
Say again?
Do you think your method has the ability to tell apart different types of cancer, as physicians usually require biopsies as well to tell apart the types of cancer, as treatment can be very different?
Yeah, so as I showed on some slide, we have a number of blocks for different issues. So, and to answer your question, the answer is yes. But there are not a lot of buts. So, for example, if we use the tissue samples that are with a high amount of blood, so thus we need change the wavelength sometime, because the green light, for example, will be absorbed quickly. And we need, to find the optimal wavelengths. And then, if we do that, so we obviously link the cost of the system, because the laser diodes and detectors, we should keep the constant or reasonable price. So that's
but I think the question was more about can you tell the difference between Barrett's esophagus and something else, a different type of.
Oh, that way. Okay. So yes, so they will be on a different position on the Polarization in our case. So imagine, so if you have, let's say optically active medium more than others, so it means that the signature will move on that way. If it's birefringent, so it goes other side, of a Polarization, and depends on which tissue is. Have what properties, so the difference will be visible. So, but we didn't consider that in a way to differentiate what tissue we see. So that might be the one of the way to answer. But my understanding also that, because we focused at the moment on the blobs, and when they prepared the blobs, that's like a dry tissue, and the optical properties of that tissues have no relation to the fresh tissues. So and thus, if we discussing, okay, so how these optical properties relates to the in vivo ones, you might do the differentiation of this on the blobs, but you will never possibly see that on the fresh tissue. I don't know, something like that.
Okay, so maybe we should continue. Oh, yeah.
What accuracy do you have?
Accuracy?
Yeah, of the diagnosis.
And in terms of what? So how many samples?
Yeah.
Okay, or in terms of, you know, how many cells, cancer cells we can see, you know, in a cell culture of, you know, normal cells.
No, like cancer, non-cancer, like positive, negative.
Okay.
diagnoses.
I'll show you. Okay, so you see here, we're able to clearly recognize this concept and non-cancer part, but of course there are always some area that they can overlap basically on the areas of there, or when on the boundaries between cancer and non-cancer. And it's at the moment is because when we focus beam, so the beam actual diameter, it could be takes partially cancer, non-cancer tissues, and thus we have always the gray area. So, but in terms of this picture, the resolution, well, it could be like, I don't know, 100 microns maybe. I think it really depends on our diameter of the focus beam.
But if you have a say, healthy tissue,
Yes.
what would be the spread on the Poincare sphere that you would get from that for different samples of tissue?
Well, it will be very much singular. So, and I have another presentation when we did on some chicken skins or some other tissues, like to see how it changed with the application of optical cleaning. So we're able to see how it changed again. So there is a matter of initial incident and detection. So that's when you're able to put your mirrors and diagnostic objective and mirror in a way that you fixed the position of changes on Poincare sphere signatures. So then it will be in this hemisphere. So if it goes there, so for us it means it's tissue birefringence. So if it goes other side, that means optical exit. So, but this will more or less relates to scattering and anisotropic scattering, forward scattering and radial scattering.
Igor, can you elaborate on why you want to use the Gaussian beam if this works?
Okay.
What new information does that add? And also, how do you decompose the scattered LT beam into its azimuthal components or this?
Okay, so again, why laser Gaussian beam? So when we eliminate with laser Gaussian beam, so we have a huge amount of states of polarization that come in with the different phases, right? So, and each of that will show us the signature on Poincare sphere. So then it doesn't matter, you know, how the sample orientation will be, you know, positioning, because we will see with one of particular polarization, we will see cancer or non-cancer, and other will change possibly because of bifringens or non-bifringens. For example, when we do this with the Euler matrix, we need to do several measurements in different, you know, orientation to avoid the bifringens influence on the signal. Or it requires a long calculations to find out, okay, so why the signature is changing. With the laser Gaussian beams, when you have all the possible orientations, so you will see the changes on the Poincare sphere, like a sort of, I don't know, figure that will show all these stages, and we believe that at least one will be related to the cancer. Another could be just.
So you're using circularly polarized, the way you describe it, isn't that radially polarized like you think?
Pardon?
You're talking about radially polarized like really.
We consider different one, it's just an example. So because there's also questions, okay, which one LG beam with which parameters is ideally to use? So at the moment it's more or less like studies, okay, so what we're actually able to see with like a Gaussian beam when it propagates through dispersive media, like tissues. And I can't tell you, okay, so which combination of LG and how we could detect it will be, for the cancer detection. So we're trying to find out, but we think it's have a future. At least nobody trying to consider, the propagation is multi-spectrum. Yes.
This is a paper from. Sorry.
Concerning or relating to this question, wouldn't it be cheaper to scan the different polarizations just to have a filter, a polarizer that's turned and then?
Well, I think obviously that for the just circular polarized light will at the moment might be cheaper to make the diagnosis, but with the development of this technologies and liquid crystals, detectors and modulators and so on, so I'm not sure, so but perhaps it will be the same price. We'll see. Yes.
I have a little general question. So when we use microscopy-based systems for optical biopsy, we get a bit of resistance from the clinicians as we ask the surgeons to be pathologists, and they're not very happy with it. But here it is sort of an indirect way of measurement, so you show, you grade whether it's normal or cancer. So are they happy to, do you know if they are happy to make a decision based on that, just without actually seeing an image?
Right, okay. So we possibly was more lucky than you, so because we're working with the pathologists who also do teaching. And what, for example, I was surprised that there are no actual course that will give the material and teaching or experience how to differentiate cancer and non-cancer. You should take some different courses, and together you can be trained after some actual training, so you will know how to differentiate. But those people who give the students that's pictures and explaining how they should make the judgment cancer non-cancer, so they're not maybe those who do actual operations and works in the laboratories. And again, my impression that those who work in that daily, they have, it's like their own business, and in that point of view they don't want to share it for free. So, but if you would employ them like a consultant, they will be very happy to work with you and share the data. So that's what I think. No, that's from my practice, but I don't know, maybe in your hospital is a different. So, should we continue?
Okay, let's continue. Yeah.
Okay.
Thank you, Igor.
Okay, so, and when we spoke and when we discussed all the previous diagnostic techniques and properties of tissues, we talk about the tissues like it's the solid or non-dynamic medium. So it means nothing is moving there. In fact, we have blood flow, we have lymph flow, we have some changes within the tissues. And one of the parameters that we consider also that could be used for assessment non-invasively optical properties of tissue is the coherence of light. And we consider that through the so-called dynamic light scattering. And I will talk the rest of my part of these lectures about this dynamic light scattering and coherence properties of light. So we briefly mentioned the coherence when we considered the two waves interference, and we discussed that, okay, the coherence is important when it's short coherence and when it's long coherence, so we can manipulate with the interference term. But what is the coherence? How many of you were, and what is your vision? What is that? How do you imagine what is that? Can you explain me what is the coherence is?
It's temporal and spatial coherence.
And what is that?
So in space, there is the light at one point in space, basically. And
okay, I'll tell you my understanding what is the coherent light is. Okay, so that might be not ideal. So, but it's coming from the laser physics view. Okay, so, and I will refer to the second year, first year physics description of how the lasers really work. So let's us consider this classic laser like a gas laser. So we have basically the we have a active medium and resonator. So it means here we have two mirrors, okay, and we pump this active medium with energy. That could be temperature, that could be some energy. So, and when we pump this medium, so they generate the photons, and photons like started to go in the different directions, and we're still pumping. Okay, we're pumping and pumping, and that photons that produce they stimulate others, and but again, so they have a plenty of directions, but because we have the mirrors here, some photons will come to the mirrors and reflect. Okay, and we're still pumping. We're pumping and pumping, and then more photons will go from mirror to mirror. And then we will come to the stage when we have resonance, means we will have the stable wave between these two mirrors. And then we will take, little diaphragm in opening. And then laser is lasing the light. And you see, so we have the stable wave with a lens like that. And that is coming, and we called it coherent lens of laser light. Okay? So it means after that lens, so the phase of this, wave is changed. That's my understanding of the coherence lens. Okay? And then, if we're thinking about the coherent properties of light, so we should take about this temporal coherence light, means when the light propagates on time, so and we see that it's perfectly coherent. But we also have the spatial coherence, means that when it propagates, it could be non-coherent, or the actual sizes could be also, less or longer coherent. And again, we have a number of different light sources. We have white light, we have sunlight, we have expensive lasers, we have less expensive lasers, we have laser diodes. And what is the coherent properties? So for the very good lasers, let's say, so there could be nearly infinite coherent lens in terms of temporal coherence lens. For white light, some people would say there is no coherence. There is, but it's very, very short. So maybe 1 or 3 microns. So, and the laser diode that used like also quite short coherent lens, but longer than this one, like 10, 15 microns. And we have also lasers that might have a good temporal coherence lens, but not special. Well, and the question, okay, so why the coherence is important? And for some years ago, so we considered the this so-called this fundamental phenomena of backscattering of light that associated with coherent, and it's known as enhancement of coherent backscattering. And what does it mean? So basically, this enhancement of coherence of backscattering is represented as a peak of radiation that's scattered. But why it's happened? And I think it's better to show it's only just this little movie that we. It's a bit slow. Okay, so let's just consider the multiple scattering medium, and we illuminate it with a plane wave. Okay, so, and if we consider how this partial component of wavefront is propagated through, which you can do with Monte Carlo, obviously, and we can see this in the, let's say this how the photons propagate through and coming on the surface from a particular point. But as we consider the plane wave, so theoretically, we can say that, okay, so there is always, we can find another part of this wavefront that will propagate on the absolutely same trajectory and coming out, you know, in the that point. And if we have absolutely the same trajectory, that means that our output wave will produce these sources, and we will see on some point destructive and constructive interference, as we discussed. And what does it mean? If we will just count the intensity, we will see enhancement or, you know, decreasing of the system. And thus, we can consider this as a, let's say, point sources. And again, if we do this 2D Fourier transform, we can see that's sort of angular pattern distribution. But again, that was for one trajectory. If we consider a number of them and see the formation of the multiple of signal in a multiple scattering medium, so you see so many photons coming. Each of them produce slightly different enhancement of backscattering. And since we will be able finally to observe the peak of that scattering that known as enhancement of backscattering. Actually, this range of angle is very small. It's like about 2-3 degrees, maybe 5. Okay, so, but again, so that's, yes. No, okay. So, and that was the one of the well-known wave phenomena that associated with multiple scattering and coherent properties of light. And okay, so, and for a number of years there was a discussion, and we did try to use it for diagnostic purpose. And the idea was, okay, so we can create a very simple technique that we're able to find based on that signature the particular position of camera and see also the samples to see, you know, is this coherent properties could be used for detection of the, again, the cancer and non-cancer tissues. Not the slices, but again, the thick tissues. And, okay, so when we saw that, okay, so we were able to see that the normal tissues are more absorbent and or less scattering than tumor tissues, and we were able to see some signatures associated with coherent properties, but were not able to, let's say, be so specifically use it for cancer detection. The other way to use this technique is to see the slope of the cone of coherent backscattering, and could be used as a measure of cancerous or non-cancerous tissues. But the problem is that this variation of the slope is very, you know, in a very short, let's say, the band of measurements, so we're not able to do it with a very high resolution. So, but then, okay, so we consider, okay, so if coherent light propagates through the medium, when we have some dynamics. means what dynamics? So, oops. Okay, so if we consider, let's say, skin or brain or whatever, so we always have the number of blood vessels, and through the blood vessels, the blood is leaking with the, with a different way. Some vessels have, the aggregated blood, some, let's say, capillary loops, when the blood propagates one by one. And the question, okay, so how we can measure or estimate that? And we also consider that the coherent properties of light could be used for that purpose. And that's, we come into development and use so-called dynamic light scattering technique, which is actually based on this so-called photon correlation spectroscopy that's known for a number of years and originally used for measurements of the size of the particles. So how it basically works, so we have a laser with a high coherent lens, and we illuminate the sample of interest, and then detecting light on any side here, we see, and we used in that case photomultiplying tool. Means this very precise measurement we see counting signal in terms of single photons. So, or we also use this the avalanche photodiodes now, because they have a similar or even better sensitivity. So, and there was a number of applications of these technologies, and a number of companies developed these so-called correlators that were able to be used for detection and analysis of the scattered light, and explain, how the size of the particles is changed. And I will just explain, okay, so how it works briefly. So, okay, so in terms of particle measurement with dynamic light scattering, so it is a way to illuminate the sample on with the system that's shown early, and we will be able to see in time the changes of speckles on the screen. So, other way, what we see. So we illuminate the tissue, and on the detector we see the intensity fluctuations. There's a big particles. So then, when we have the small particles and we illuminate the sample with the light, and we also see the intensity fluctuations. And the question is, how different these fluctuations are. So from that picture, so we're not able to say for sure what is the difference, and that's what we really measure. So, and it's not always we able to use this scattering signature for a quantitative measure. Okay. So the other issue is, okay, we have, let's say, Brownian motion or fast motion of particles. And then if particles aggregated and stick together, they have slow motion. And when we illuminate each of that sample, we also see the intensity fluctuations. But this intensity is not useful for us. So we see that some differences, but how we can quantitatively measure that? And thus we use correlation analysis. So what we do, we replot each of that intensity in terms of correlation function. And the slope of correlation function is a measure, quantitative measure of this difference between this and that, or size of the particles. And how it really works. Okay, there is an important issue. So when we do any measurements in optics, we measure intensity. And when we do interpretation of that result, we operate with the electric field definition. And from electric field definition, we're able to say, okay, so this electric field changed because of that, that, and that. But if you remember, so intensity, when we define intensity, is the field, and complex conjugated field means that the phase part is missing in intensity. Right. And only because of so-called Gaussian approximation that also is known like a side relation, we're able to link the results of measurements of intensity correlation function with the field correlation function. So, and with this relation, so we're able to link the result of measurements with the theoretical model or approximation that we use here for, again, for extract the information about the motion and size. So, and of course, that very much started from the investigation of Brownian motion, and just some facts that at first the Brownian motion was observed again by Robert Brown, but he didn't understand what actually he saw. And then again, so there was some discussion about that, and they thought, okay, so the important result was the thermal molecular motion in the liquid. So, and only in this year, okay, the mathematical theory of Brownian motion was developed by Einstein, and actually it was partly for again this work he would receive the Nobel Prize in 1921. Okay, so and here again, so what I want to mention, so okay, so when we have a suspended particles, so the suspended particle is again constantly and random, like bombarded from sides by molecules and of the liquid. Again, and if the particles are very small, the hits it takes from one side will be stronger than the bounce from other side, and causing again to jump. And these small random jumps are what make up Brownian motion. This is just a definition or explanation from statistical mechanics. And again, follow this, so we can, so on so-called the Stokes and Stein relation, so we're able to define the diffusion constant, diffusion coefficient that describes the, the motion of particles within the sample. And it relates to temperature, viscosity, and radius of particles. And K is the Boltzmann constant. Okay, so then when we consider light scattering, so we know again initial polarization, and we know the final polarization, and we're able to define this wave vector, and thus we're able to present the diffusion constant for Brownian motion in a way that can be explained through the relaxation time and scattering vector. Okay, and here is what is the scattering vector R. So it means we're able to define the Brownian motion through the totally independently from the previous definition. Okay, and they means absolutely the same thing. So this time is determined from the experiment and relates to the coherent properties of light, and thus we're able to, from the measurement, we're able to make the characterization of Brownian motion in terms of, again, temperature or radius or viscosity. Okay. And then the question, okay, and what we can study with the dynamic light scattering, and actually. If we know how, so we can do the studies of many interesting, physical and chemical and biophysical phenomena, and nanoparticles and liquids with some glass transition, polymers, gels, DNA, many others, bacteria, viruses, whatever, and we're able to use it for measurement of particle size, radius of gyration, size of globulin, and many other things, diffusion, relaxation, dynamics, and then just one example when we consider the aggregation of different, let's say, red blood cells. So you see, so the different parts of this correlation function could be used as a quantitative parameter for different aspects. Some of the could be used from the let's say aggregation, and some could be related to the even shape of the particles. In our case, we wanted to use it for again for diagnostic purpose, and okay, so and we thought that okay with the that experimental system we able to use it to move to observation and quantitative assessment of measurements of blood velocity within the skin or other biological tissue. So what we need for the, we need the laser source with the no coherent properties. We need computer with obviously correlator and with the very sensitive detector, again, as I mentioned, photomultiplying tube or avalanche photodiode. And we actually start these initial measurements a long time ago when I studied in the Britain Child's lab, and we did with David Boss, who's also here. So the measurements on our own arms to see how we can adopt this technique. And of course, those time we more focused not on the skin but on the muscles. And the reason was because Brigham Chance was involved in some sports medicine projects, and he studied really how the muscles relaxation and some blood influence in the muscles was important parameter for him. And we thought that this dynamic light scattering, or we call it also diffusion-based spectroscopy, so for some reason, because we use diffusion light for the 6 samples, we thought that it will be one of the possible technologies for that use. And what we're able to see, so again, we measured the correlation function, intensity correlation function, and through the side-shift relation, we transformed it in a field correlation function that could be described analytically. And this function is described the distribution of trajectories of photons within the tissue. And thus, we're able to analyze this displacement based on the slope of correlation function. And if you see, so if you just simply replot these correlation functions in a semi-logarithmic scale here, so that gives me very nice linear relation. That means that it's exponential decay, and okay, so and we can use it for the analysis. So, and also we did the standard occlusion test, and we found very interesting relation with known physiological data, like when we have a normal, so we have this slope of correlation function, basically like that. So as soon as we make it suppression, so the slope is dropped, so means the blood flow is going very slowly. And then when we take off the cuff slowly, so this slope is coming back to normal and even higher, so because we have the hyperemia, because when we waited here from about 30 minutes, so there wasn't enough on tissue, the oxygen, and blood is going quickly to, to compensate the oxygenation one. So also here's an important note. When we do the cuff test, so with a standard, technique when we're pumping that. So if you think from the physiological point of view, the veins and arteries, they located closer to the surface of the tissues. And arteries basically deeper in the tissues. And when we do suppression, so we first will, suppress the blood, the veins, but the blood from the arteries will still pump to my parts of the measurement, part of my hand where I do the measurements. And what it means? That means when on a time when I do the measurements, the blood volume inside the point of measurements will be changed. And these changes could be, affect significantly the results. And thus we did very quick suppression, specially designed there. Okay, so the other issue, so how we can predict what the actual velocity in there. And we of course also implemented this Monte Carlo technique to understand, we're able to predict the actual path length from input to output, and then we have these measurements, we know how this could be changed, and we're able to assign the displacement of each particles here, and thus if we're able to assign that, so we can basically fit and estimate the results to find out these dynamic changes on the detector. So also, if we consider, we always talked about the Brownian motion, and but if we consider this diffusion time correlation function, we're able also to, in the equation that describes that, so we're able to introduce not only Brownian motion but also the flows parameter, and that and thus we're able to describe it analytically, but we want to find to the way to calibrate what we're actually able to see from this the slope of correlation function. And okay, so if we consider the flow within the, let's say, phantom or blood flow within some sample, so we're able to measure that and we're able to predict it with Monte Carlo, as I mentioned before, or with this equation for the simple medium, and potentially, so we can say that, okay, for the phantom studies, we're able to find out how the slope of correlation function is changed with the increasing or decreasing of velocity. And thus, from that, we can validate this phenomenological model, or, you know, fit it to modeling technique to with the reason, okay, how we're able to say what is the velocity for that slope or for that slope. And okay, so we've done this preliminary modeling studies and phantom studies, but then when we came to the let's say to the actual let's say living tissues, so we thought it's not so easy, and we decided to let's say cross-validate it with the actual measurements, with the known techniques. And for that we developed the technique when we used the one part that uses correlation function, and the other part that makes images of actual blood flow. And we did try to cross-validate and find how we can, you know, extract the useful information from that measurements using the actual data of measurements. And this is actually our main patients. So, and we use this very convenient subject of measurement, because you can easily stick it and it will be stable and no any motions or artifacts associated with the animal breathing and others. Okay, so and for see the imaging in there, so we use so-called laser imaging again, laser contrast imaging or laser scattering imaging. A number of names of that, but actually it's one of the, let's say, extension of this dynamic light scattering, and it is a bit different experimental system that here we use the CCD camera instead of the fiber optics or focusing light. And okay, so how it works really? So we illuminate the object where the blood flow is moving. So, and CCD camera will accept the images, and we will see on the camera some images like that. So, but in fact, what I showed before, so it's only the final result. So first of all, to get this result, we need to calculate so-called temporal spectral contrast, which is actually we have the standard deviation on the CCD intensity counts at each pixel, and again during the number of frames, and n is number of frames that, you know, again equate for again, and x and y is the mean value of CCD intensity contrast in the same pixel. So, and okay, so that's what we're illuminating and what we saw as a raw laser imaging. And okay, So, and then we collect a frame of images, and then we're able to, again, calculate intensity fluctuations in each speckle, find the mean number, and again, we see this definition. We're able to produce a very good image that shows us each vascular pattern. So, and of course, then we can do it with some color coding. So, again, the main issue to combine or consider that. So, and then, you see, so when we do that, so we found, so the movie is not working again. Okay, so basically it shows that we're able to see the slope of correlation function, and each slope could be linked with the particular flows in there. And we use the some smart mathematics to you know, to combine that. So okay, so and okay, for that purpose, we also combined our imaging system with the other technique that are able to give us exact show exact flow or vessel distribution within the animals, and we're using also it for validation of both techniques with the fluorescence imaging, which is also quite good for that tissue. So again, that's what the light scattering imaging gave us. From raw imaging, we're able to see the vessels, and okay, we're able to change the acquisition time and see these variations within within particular places. So, but again, so there are no fluorescence markers. So, and this actually technique is very, very sensitive, and I would just want to demonstrate how sensitive it is. Okay, so when I again was in a Britain's lab, so we did the first measurements on the animals. And we found that, okay, so that when the animal alive and when, sorry, animal dead, so the slope of optical correlation function exists. And it drops, and we're able to see the slope, which is now zero, like for after 2 hours. And I wasn't able to explain that at that time. But then when we started to calibrate it against laser imaging, so we saw a very interesting picture. For example, this you see the motion of blood in real time when the animal is dead on the brain. So, and we see this in the speckles mode. And we see that it's not Brownian, it has some random directions, and again, so sometimes it's change direction. So, and obviously that when animal is dead, so the temperature and pressure distribution in the body change, and system trying to equalize the pressure across the body, and these flows are expectable. But recently we used the same technique for seeing, okay, so what happened with the brain. Okay, so and you see, so this animal is dead, and we see that the activity within the brain is localized on some area, actually is here, and this localization could be observed for during the hours, at least 1 hour, and you see, so this is actual minutes, and the seconds what we observe. And now we're going to check, you know, how this localization is, you know, linked with neuron activities. So, and who knows, might be when some people say when after the clinical test that they saw the white light somewhere in there, so that might be the explanation. I'm not sure. So,
how do you do the experiment for that?
That was the one.
Good luck with the ethical permission.
Yeah. So, and okay, so and the other one that I very like the results. So imagine, so with this technique, when we're able to see this dynamic light scattering at normal conditions on this patient, and then what happened if we focus of light on the particular blood vessel. So you see, so with the laser we can temporarily stop the blood flow in a particular blood vessels group and increase the velocity in the other. So, and this could be used as a technique for manipulation potentially of blood flow within the tissues. So, and of course, one of the our interest was some tumors, and on the mice, it's very easy to consider some regional perfusion on angiogenesis within the tumors. But it's not exactly our area, so we just demonstrated that we can do. One of our recent results also is interesting. So we considered how the blood flow is influenced by different chemicals. For example, here if we drop some water, so we see roughly nothing. The water is of same temperature as skin. And here we added the standard the optical clearing parameters. So we see the little influence, and when we have some irritants in there, so that's immediate reaction of vascular bed there. So
Igor, what does it mean in this green spot and there? What?
Intensity.
Intensity of what?
Intensity of what? Okay, so it's a color-coded picture. Okay, as I mentioned with this LSI technique, when we see this
does it mean that blood velocity is high? Does it mean perfusion is high? It means...
No, it means that, okay, so this is normal, and it will be like a perfusion with a slow, but it will, produce accuperated more, field before the vessels, like under the vessels. Okay, it's coming out from the blood, like there was a leakage. And okay, and there was a discussion about these breathing artifacts. And we also do a number of the studies, and we're trying to adopt known mathematical, physical techniques that use basically in astronomy to this biology application. And we found that, okay, so that we're able to make the images quite stable. Basically, that's everything that works for in the future to transfer that to stroke and stroke prevention or neurosurgery, new drugs development. But again, so when we work with the small animals, there are a lot of some artifacts associated with emotion and vibrations, and we worked on how to avoid that. So, and for some reason, again, we considered the combination of this laser speckle intensity with the fluorescence one, when we simultaneously able to see the fluorescence, for example, site when it's injected in the lymph flow, and we see changes of blood flow that we don't need to do any injections, and this it could be also done in a very cheap way. So using this again cheap lasers and laser diodes. So and we see actually comparable time of real measurements. So, okay, so wait a second. I think there's some okay, so there's some duplication of slides that I showed earlier. Okay, so, and finally we're able to produce this dynamic fluorescence imaging through the intact cranium, so it means we don't need to cut any skin or bones. It works mostly for the small mice, but again, so we're able to produce this clear pictures and...
Was it a nude mouse? Like, was it a fur or...
Pardon?
Was it a nude mouse? You said it's a mouse.
Yes, nude mouse, yes.
So did it have any fur?
No.
It's a nude mouse.
Yes. And that's have a big interest for some physiologists who work with us, so I'm not able to maybe to make a comments about this physiology, but they have a for them, the different group of vessels and reaction on some phenomena is quite interesting, and we was very proud that this actually this picture that we got with this technique was recently selected for the cover page of journal Biophotonics, and those of you who have an interest, so you can see the description of details in this journal Biophotonics issue. So, and this paper about this simple TOVI, we call it experiment. But basically, again, to combine this dynamic light scattering with fluorescence makes a very powerful tool to observe the vascular reaction on a different application. And we also did it for tumors, and we're able to see them in tumor surrounding and blood vessels and small vessels, and it's also considered like was also published in the Biophotonics early, and then we switched to the brain, and with brain I think we have a more attractive results. I think that's it for.
Thank you, Igor. I think we've already had quite a lot of questions, and we're quite a bit behind for lunch, so I think we'll go straight to lunch, and Igor will be around if people want to ask more questions. But, thank you for that.